So this video is a description of the first order integrated rate law. So recall that the rate law for first order is equal to the rate constant times some reactant in this general equation of just having one reactant raised to the 1. We don't write the 1, but we know that it's there. Now, when we look at reactions, if we have some reactant A versus time, if you saw the zero order integrated rate law video, you saw that this was a straight line going down. And that's true for zero order, but usually there's a curve there. Usually there's a lot of action going on at the beginning. Usually there's a big change in concentration versus unit time at the beginning. And then the change in concentration flattens out, right? There's not a whole lot of change versus time as time goes forward. So usually you get this curve. Now, working with curves, I mean, we can do that, but it's a lot easier to work with straight lines. So there's an interesting math trick that we can do here. Whenever we have these exponential decays, what we can do is we can change the concentration. Instead of plotting the concentration versus time, we can plot the natural log of A versus time. And sometimes when you do this with these curves, sometimes you'll get straight lines that look like this. Working with straight lines is easy. We like doing that because we can do this y equals mx plus b. And so we can get our integrated rate law by using this equation. Y is going to be our ln of A. M is the rate constant. Because the line is going down, left to right, going down, we'll put a negative sign. X is the time. B is the y-intercept. So the line crosses at the initial concentration of A. So what you're looking at here is the integrated rate law for first order reactions. Now again, what does this tell us? Well, it tells us that we can find the concentration of A at any time as long as we know the rate constant and the initial concentration. Now be careful with the first order integrated rate laws, because the concentration of A is inside the natural log. And so we have to do a little bit of work to go find the concentration. We have to get rid of that natural log, which is something that we've done earlier this semester, so you know how to do that. There's another way to write this. So there's a lot going on here. Let me show you an easier way to write this. This is what I like to do. So I'm going to rewrite the integrated rate law for first order. And I'm going to set this up like this. Subtract natural log of A naught on both sides. So this cancels. So let me rewrite this to clean it up a little bit. There's a math trick here. I shouldn't say trick, it's a rule actually. There's a math rule with natural logs. Natural log of A minus natural log of A naught, we can rewrite that as a ratio. We can rewrite that as ln of A over A naught. And so natural log of concentration of A minus natural log of concentration of A naught, there's a natural log rule where we can rewrite that as natural log of A over A naught. And this is still equal to negative KT. If you have these flipped, then you change the sign here. So you can write it either way. I like doing it this way, and I'm going to tell you why. Because this is a really nice ratio right here. A over A naught. This is the original concentration, and this is the new concentration. And so I like writing it this way because, let's say, for example, in a question, the question is asking you, the reaction happens and the reaction goes until the concentration is 1/4 of the original concentration. And so you'll get questions like that. And so if they're telling you, well, the concentration is 1/4 of what we started with, it's really easy to work with first order integrated rate law. We can just plug in 1/4, 1/4. Or sometimes, the question will tell you that there's 10% of the reactant remaining. remaining, or 90% complete. If it's 90% complete, that means there's 10% of reactant remaining. And so what we can do is, because this is a nice ratio, we can write ln of 10 over 100. And so it makes our calculations a lot easier. We can just plug that ratio in there. And so working with first order integrated rate law is not as hard as it looks. So this is the equation I would recommend. Okay, just a quick word on the half-life. The half-life, remember, is the time it takes for the concentration to be cut in half. We'll call this T1/2 is equal to 0.693 over K. Now, let me show you how we get there. You don't have to know how we get there, but I just want to explain how we get to this equation. So if we go to our integrated rate law, remember, we want to know when this value is equal to A naught over 2, right? 1/2 of the initial concentration, when the initial concentration gets cut in half. And so this actually winds up being pretty simple. If we rewrite this, just substitute the concentration with A naught over 2 and divide by this term, A naught. Well, the A naughts obviously cancel. And this is equal to negative KT. So this becomes natural log of 1 over 2 is equal to negative KT. The natural log of 1/2, let me continue over here because I'm running out of space. The natural log of 1/2 is 0.693 is equal to negative KT. Divide both sides by negative K. I'm sorry. the natural log of 1/2 is negative 0.693. So yeah, those negatives cancel. And so the half-life is 0.693 over k. So let's do a quick recap here. So for the first order integrated rate law, if you plot the natural log of a versus t, that will give you a straight line with this negative slope. If we use the y equals mx plus b, this is what the integrated rate law would look like. Now we can rewrite this so that we can write the integrated rate law like this instead. And I highly recommend you do this because this is going to be a lot easier, especially when we go over to the nuclear chemistry chapter, because those nuclear decays, radioactive material, the nuclear decay is first order kinetics. And so we're going to be using this equation a lot. The half-life is equal to 0.693 over the rate constant. Now this is important because in a lot of questions, they'll give you the they'll give you the half-life, and we need to go find the rate constant. And I'll give you an example of that here in the next video.